Welcome to a lesson with Dr. Powell. Let's look at how we can see that the Hom functor of a limit is actually a limit of Hom functors. So let's let L be the limit of a diagram D. And if you take this diagram D and you apply a Hom functor to it, like this one where we're inputting things right here, the effect is to get another diagram because Hom is a functor and it preserves commutativity of diagrams. So from here to here, we have a commutative diagram here with the Homs. And what we'd like to know is we'd like to know that this guy is the limit of that diagram over here. And we know that this is the limit of this diagram over here. We've only drawn two objects in this diagram. Let's imagine this diagram is much bigger, but I just did two for illustration purposes. Okay, now, given any object P in the category C, such that you have morphisms from here and here that make the diagram with just P and the diagram D into a larger commutative diagram, then the universal property of L states that there is a unique morphism that goes from P to L, such that if you can combine that morphism and the ones from L into D and these ones right here, and you get a really big commutative diagram. But there's a unique morphism that does that. There exists one for any object P that has this going on. So that's kind of what makes L a limit. We want to see that the same basic idea works over here for the output of this Hom functor when you plug in L. So the way that we're going to do that, okay, so let's suppose that we have a system of elements in a diagram from S to here, kind of extending this diagram back to S along these different paths here. And we have a commutative diagram. And we're going to take a system of elements, starting with S and looking at the destinations of S everywhere in this diagram. Now, no matter which way we go, through which arrow paths, all the destinations should match up. Okay, so we're going to look at that situation and see what it looks like over here. So S is going to be sent to something, and its destination, whether we go this way or that way, should match. So if we go this way, let's suppose it goes to Fi. Then Fi is sent by just lengthening Fi, or kind of extending it, composing it with this guy. That's the way this Hom functor or this morphism would work right here. This set map would work. So we extend that. And so this should match up with wherever this is sent. Well, so just saying that we have a system of destinations that match over here between from this one single element is the same thing as saying that this composed with this is this. Basically, it's the same thing as saying we have a commutative diagram over here, a corresponding commutative diagram over here. So, well, if we have a corresponding commutative diagram over here, then that means then there exists a unique morphism from P to L that makes this all be a big commutative diagram. Wait a minute. So that means there exists a unique element in here that maybe we could send S to, and that's a unique map. We've defined it in a unique way. So let's let S be sent to that guy that's right here. And let's take a look at what that means. Okay, so the destination of S to here, which is right here, if we take that and we map it down here, that's like extending this by this morphism right here, then we should get the Fi that we got right here, which is the same thing as saying that this part of the diagram commutes. Similarly, it would commute everywhere else here, which means what we've done is we've created a unique map that makes the whole thing a big commutative diagram, which means that we've actually guaranteed that this actually is the limit in sets of that diagram down there. In the next video, we'll discuss how this equality that we've just barely come up with between the limit of the HOMs and the HOM of the limit is natural, and what that means. Thanks for watching.